Hello, everyone. Today I'm going to start covering this textbook, Nonlinear Dynamics and Chaos by Strogatz. This is an excellent book on nonlinear differential equations for those who are looking for a gentle introduction to the subject. It reads like a novel, and you only really need some basic background in differential equations and calculus to read this book. So I highly recommend you grab a copy and follow me through the book during this course. I plan to do this very high-paced way, and so the goal is to cover a chapter of this book every day, and hopefully we'll be able to finish the book in 12 days. So pretty ambitious, but let's see how it goes. So let's get started. Chaos theory. So, what is the study of chaos? Turns out you don't need to know the answer to that until about chapter 9. So, I'll just tell you right now that we're going to study nonlinear differential equations. We're kind of going to look into methods, geometric methods of gaining qualitative behavior of your solutions. If we start off with a differential equation, dx over dt is equal to 3x. Okay, so we know, hopefully, that this is a linear first order differential equation, and we can solve it, right? This is a basic equation you would have learned in differential equations. You divide by x here and multiply by dt. And then so this is how we separate the equation, and we integrate both sides here. And we're going to get natural log of x is equal to 3t plus c. I exponentiate both sides. Whoa. And I get x is equal to c e to the 3t. Okay, great. And then if I have some knowledge about my initial conditions, I can solve for the constant there. So turns out this is nice, and this is a basic exponential growth model, but it's really like the bare bones, most basic case you could possibly give someone, right? There's no time dependence. And in fact, we're not even going to discuss time dependence, okay? And I'll explain why in a little bit later in this video. But now, if I try to make this thing nonlinear, okay? So if I have any term that's not x or a constant, all of a sudden there's like a whole swath of problems, right? So for example, dx over dt is equal to sine of x. Now, this equation is still separable, but as you can see, the integration immediately becomes very, very gross, if not impossible. So if we try to integrate this thing, let's separate it. Dx over sine of x is equal to dt. We integrate both sides here. We're going to get t plus c. And then the integral of 1 over sine of x, I'm not going to go through that derivation with y'all today. Luckily, Strogatz has solved this. And according to him, this integral becomes negative natural log of absolute value of cosecant of x plus cotangent of x. Awesome. Okay. And then if we apply some initial conditions, say x is equal to x naught at t is equal to 0, we can solve for this integration constant. But this is not that useful unless we have like a graphing calculator, right? And even then, it's kind of difficult to dissect what's happening here. The reason is because the solution is not solved directly in terms of x. We have an implicit form of our solution, which is t as a function of x, and we want to kind of reverse that, which sometimes is impossible. Secondly, this is such a complicated composition of functions that we have no idea how this behaves, and we'd have to sit and think about it for a long time to like figure out what this actually is doing, right? Turns out there's a lot simpler way to analyze this equation, okay? And this is kind of going to be an overarching theme in this whole book is we're going to solve these systems, almost just completely determine all of their behavior without actually creating an analytic expression for the solution. And so this is what's called a qualitative or geometric method for solving the differential equations. So let me show you how it works. Essentially, if I have an equation x dot, all right, and x dot, just for those of you who don't know, is dx over dt, is equal to sine of x. I'm going to start by graphing this function, okay? And I'm going to just term this function f of x for generality. Okay, so our general equation is going to be of the form x dot is equal to f of x, which is a homogeneous equation. Notice we don't have time dependence on the right-hand side, which is a very important distinction. If we have time dependence, we can no longer apply this method as easily. So essentially, we just plot this function as a function of x. Okay, so sine of x, hopefully that's what it looks like. And we have x and x dot here. And this is what's called a phase space. And now I claim that just by drawing this graph, we can see so much into the behavior of what actually happens in our solution, okay? So our solution is, remember the solution that we're looking for is x of t, okay? And this lives on the real line, okay? So this lives on the x-axis. And essentially what we have is as time changes, say here's x naught, and then the solution curve is just, it's going to like, the solution is just going to drift along here with the function of time, okay? And essentially x is going to move along this line, the sum function of time. And it turns out that in this autonomous equation here, okay, so with no time dependence on the right-hand side, this flow is only going to be monotonous. It's never going to, like, for instance, like start here, start flowing, and then go reverse direction. That's physically impossible. And that's because if you think about this x dot here, okay, is determining the direction of the flow along this line. And since f of x is single valued, so for every x, we only have a single value of f of x, that means that x dot can only have one direction of flow, okay? And so because of that, we can never like reverse directions back on itself, because that would require f of x to have two outputs for a single input, right? Which would break the fact that it's a function. Hopefully that made sense. So let's move back to our phase space here. We can make some observations. First of all, in the region where x dot is positive, okay, there's going to be flow along the line, which is conveniently our x-axis. And our trajectories are going to flow in, when x dot is positive, they're going to flow in the positive direction, okay? So our flow is going to be, I can see that it's going to be to the right by noting the fact that x dot is positive in this region. Similarly here, we have x dot is negative, okay, and so the flow is going to be to the left. So immediately I can just tell the exact direction of the flow along the x line. And now you see that they're going to converge on this point here, okay, which should be pi. So this should be pi. Essentially, f of x equals sine of x goes to 0 at x star is equal to pi. So we call this a fixed point. And we're going to be dealing with a lot of fixed points in this course. Now, fixed points can have certain qualitative properties. they can either be what we call stable or unstable or semi-stable. So in this case, this fixed point here at pi is stable. And that's because the trajectories, the solution curves, are flowing into it. Okay, so it's acting like a sink, and it's absorbing solution curves. And so this would actually be a stable fixed point. Okay. The reason why it's called a fixed point is because if I start here, if I started my trajectory at this fixed point x star, I would stay there for all time because x dot is 0 at the fixed point by definition. And so I can always have a solution which is just x of t is just equal to pi for all time, just a constant solution. And that's called the equilibrium solution or the steady state solution because it doesn't change with respect to time. And this will always occur at a fixed point. Okay. Now, there's a few things we need to think about here. So observe that there's multiple fixed points in the sine of x curve. We have another fixed point at 0 and another fixed point at 2 pi and negative pi, etc. We actually have infinitely many fixed points. Now, if I look at, let's just say the fixed point at 0, okay? Notice immediately that the flow is going away from that fixed point. And if I were to complete the drawing here, I have a net flow on this x-axis that is diverging away from the fixed point. So this is what we call unstable, okay? An unstable fixed point is one that's repelling. So solution trajectories that are close to it like get repelled away from it in that manner. So let's call this x star is equal to 0 is an unstable fixed point. And now let's do a little bit of more theory of how we can determine whether or not a fixed point is stable or unstable. Okay. And so if I look closely here, I can make this observation, which I'll make with a highlighter, I guess. If I look at the slopes, okay, so if I look at the slope of f of x, this drawing is getting a little bit overused. It's all right. So let me just redraw it. If I look at the slope of f of x here, I can see that f of x, f prime of x star is less than 0, okay? And it turns out that this is stable, and at the unstable fixed point, f prime of x is positive. And this is actually an important feature, and this will always be the case, okay? So we can always determine the stability of a fixed point by just looking at the sign of f prime at that fixed point, okay? And this is super useful. Now let me prove this for you or give you a more mathematical reason why this is true. Let's say x star, let x star be a fixed point. Okay. And now we know that f of, sorry, not f, x of t is equal to x star is a solution. If we want to verify this, we'll observe that if I take the derivative x dot of this function, it's just a constant, so x dot is 0, which is equal to f of x star, okay, by definition of a fixed point. So we see that this equilibrium solution always solves the differential equation. Now let us perturb x of t by a small number, epsilon, okay? So the idea is we're going to start at this fixed point here, and we're going to move along the line a little bit by a factor of epsilon. And we're going to try and see, okay, if I just perturb from the fixed point a small amount, does the solution collapse back to that fixed point, or does the solution diverge away and repel away from the perturbation? And this is an important idea. Awesome. So we're gonna perturb by a small number epsilon and see what happens. Will our solution trajectories collapse back into the fixed point, or will they diverge? Okay. All right. So suppose x naught, okay, and x naught is just x at time 0, is equal to our fixed point plus the small number epsilon. Okay, then we'll observe that x dot at 0 is precisely f of x naught, which is f of x star plus epsilon. And now I'm going to use a trick where I Taylor expand this term about x star, because epsilon is a very small number. So Taylor expanding will give us f of x star plus f prime of x star times epsilon plus terms that are of order epsilon squared. Just a quick reminder, this epsilon is coming from x star plus epsilon minus x star in the traditional form of the Taylor expansion. And then here we have higher order terms that are all going to be multiplied by at least an epsilon squared. Okay, and so for small epsilon, this term becomes negligible. So long as f prime of x star is non-zero. F prime of x star is not equal to 0, okay? So, and we'll see, I'll explain why in just a second. So, first of all, f of x star is immediately 0 by the fact that it's a fixed point. Okay, and now if this term is non-zero, we can neglect the order of epsilon squared terms because they go to 0 much faster for small epsilon than just the linear term in epsilon. Okay, so we can neglect the higher order terms so long as we assume f prime of x star is non-zero. And so when we do that, there's two cases. Okay, the first case is that f prime of x star is positive, in which case we get x dot. Remember, x dot is what we started out with at time 0 is equal to some positive number f prime of x star times epsilon, roughly, because we're neglecting higher order terms. And now we can say that this is going to be the same sign as the epsilon. So this is greater than 0 for epsilon greater than 0, less than 0 for epsilon less than 0, right? And now we can see that, remember, my perturbation is precisely that epsilon. So this is a positive perturbation. We can see that if I perturb in the positive direction, my derivative is going to be positive. So I'm going to start flowing in the direction I've moved, and I'm going to diverge away, right? Same thing in the negative case. If I perturb in the negative direction, should be negative. This is negative for you guys. So if I perturb in the negative direction, then x dot is negative. And so I continue to flow in that direction and I go off away from my fixed point. Okay, so this is a characteristic of an unstable fixed point. All right, and just graphically here, we started out with our fixed point x star, and we added a little epsilon. If epsilon was positive, we diverged away. And then if we subtracted a little epsilon here, our x dot was negative, and so we also diverged away. So we get this instability divergence here. Now, on the other hand, if we have f prime of x star is less than 0, then the exact opposite thing happens. So x dot at 0 is equal to f prime of x star times epsilon, which is less than 0 if epsilon is greater than 0, and greater than 0 if epsilon is less than 0. So it's opposing the epsilon, right? So essentially the perturbance is decaying, because if I take a positive epsilon here from my fixed point, then my flow is going to be in the negative direction, the opposite sign of the epsilon, and so the epsilon is going to decay back to the fixed point. Similarly, if I take epsilon to be negative, then the flow becomes positive. And so again, it opposes the perturbation, and it flows back into the fixed point. So this is a characteristic of a stable fixed point, okay? And this is super important, so I'm just going to reiterate. We have that if the sign of the derivative at the fixed point is positive, then we have an unstable fixed point, always. Okay, and if the sign of the derivative is negative, we're going to have a stable fixed point. All right, so we could probably go into some examples. Okay, so let's jump into some examples here. So I'm going to pull 2.2.3 from the textbook. We have x dot is equal to x minus x cubed. All right, so the first step is to find the fixed points here. And these fixed points are when f of x, this term on the right-hand side, goes to 0. So we know that x minus x cubed is equal to x times 1 minus x squared. And I'm going to set this equal to 0. So I get that the fixed points occur at x equals 0 and then plus or minus 1. Okay, so we have 3 fixed points. Let's determine their stability. So if I look at f prime of x star, well, let's just first of all write out f prime of x. So f prime of x is going to be 1 minus 3x squared. Now if I evaluate this at 0, the first fixed point, I get 1. So that tells us since this derivative is positive, we should have an unstable fixed point. Then f prime at 1, and in fact, 1 or negative 1, doesn't matter, is going to be 1 minus 3, so it's just going to become negative 2, which is less than 0, so this is a stable fixed point. Okay, and now let's graph this. So again, we have x dot is equal to x minus x cubed. Phase portrait here, we have x and x dot. So the phase portrait, I'm going to look near the origin. It's going to behave like x. It's going to have a slope kind of like this. And then it's going to basically, the x cubed term is going to start dominating. And we're going to have something that looks like this. Okay, and this just takes practice, like getting used to the graphical intuition here. But immediately we can see, just by graphing this, that at 0, we have these 3 fixed points at negative 1, 1, and 0. And then at 0, the slope is positive, so this is an unstable. At 1, we have a negative slope, so we have stable. And at negative 1, we also have negative slope, so this would also be stable. And then if I draw the flow along the line here, it's always going to flow towards the stable and away from the unstable fixed points. You can also observe that where I drew area, so in this region here, I drew flow in the positive direction, and note how x dot is positive in this region. In this region, I drew negative flow, right, towards this stable fixed point, and observe that x dot is negative in this region. So all of the analysis we did at the beginning of this lecture fully holds. It's just we already knew the stability of the fixed points from just looking at the sign of the derivative of f. And then once we knew, like, say I just gave you a line with just some fixed points on it. Actually, they're always going to alternate. Say I just gave you a line with some fixed points. Well, I know that my trajectory is always going to flow towards the stable and away from the unstable, like so. Okay, now let's move on to another example here. And it says you should solve it analytically, but I'm not going to bother with that right now. It's fine. So x dot is equal to e to the negative x sine of x. And this is problem 2.2.4. Okay. So for this one, again, the first step is just to look for zeros here that correspond to the fixed points. So our zeros are going to occur, e to the negative x is never 0. So it's only going to occur when sine of x goes to 0. So we have that the fixed points are at k pi. K is any integer, because that's when sine of x goes to 0. And then if I were to take the derivative f prime of x, could write it out if we really want to, negative e to the negative x sine of x plus cosine of x e to the negative x. And now you can see it's getting a bit more gross to evaluate. It's getting a bit more gross to evaluate their stability, right? Because now the next step would be to plug in k pi for x and look at whether or not this thing goes positive or negative, okay? And we can do that, but it's easier to just graph the function and do everything graphically. So observe that if I just look at my phase portrait, I have e to the negative x, which is going to be like a manifold here. So here's my e to the minus x. And then the sign is basically going to oscillate in this manifold and decay down. And I should be specific that this is like kind of going to bound the sign oscillations. And so you can see that for e to the minus x sine of x, the amplitude of the oscillation is given by the e to the minus x, basically bounds the amplitude. And then sine of x is actually what's driving the oscillatory motion. Now this again has the same exact fixed points that we analyzed earlier. We have fixed points at pi, 2 pi, etc. And they have the exact same stability. Okay, so here I have a positive slope, so this is unstable, negative slope, stable, positive, unstable, etc. And so I can just go ahead and fill in the diagram here for you. And another interesting thing to note is that if my function is always crossing the x-axis, okay, so if my function always crosses the x-axis, then, and it's a continuous function, then essentially the fixed points have to alternate in stability, okay, because every time it crosses it from negative to positive, it'll have a positive slope, and then it'll be unstable, and vice versa for going back down to the negative side. So we should expect that fixed points should change, like stable, unstable, stable, unstable, unless there's a semi-stable fixed point, which I guess I'll just briefly talk about right now. So the semi-stable fixed point is the case that we haven't reviewed yet, which is basically when you have a zero, you have a fixed point, but it doesn't actually cross the axis here. And so if I look at my trajectories, I'm going to be going positive in this region, and then I approach this fixed point here. But then when I perturb to the right, I'm still going positive, okay? And so notice how it's semi-stable literally, because this left-hand side is stable, okay? So it's attracting, but the right-hand side is repelling for the same reasons we discussed before. So this is what's called a semi-stable fixed point. Next up. All right, and so this example, I claim that we're done. I'm not going to go through the work of plugging in values for f prime of x. I can show you that it works by just plugging in pi here. So if I plug in pi, I'm going to get negative sine of x is going to go to 0, right? And cosine of x is going to go to -1. So I get negative e to the negative pi, and this thing is less than 0, so it's stable. Just like what we saw by graphically analyzing it. So a lot of times you can save a ton of energy and solve the problem very, very quickly by just using the graph of f of x. It's just that easy. And obviously maybe I'm oversimplifying it, but I just think it's such a beautiful way of solving differential equations, or at least we're not technically solving them, but we're understanding them. It's like we're having a conversation with them and getting to know their favorite color and their favorite flavor of ice cream, right? And that we know exactly how they're going to behave. We know how they move and how they flow, even if we don't have the exact analytic time trajectories. Now, okay, so picking up where we left off, there are some nuances to this analysis, to understanding and getting to know the qualities of these differential equations. So first little insight is we can look at the fixed points. Let's just look at here's some f of x, here's x, and here's x dot, right? And we're always going to be dealing with the equation x dot is equal to f of x for the foreseeable future. Now, if I look at the behavior of my trajectories on the x-axis, I observe that, okay, we have a negative slope here. This is stable, unstable, unstable, right? But we can also say things about the speed of the flow, okay? So notice how the speed is actually accelerating as it moves away from this fixed point. And then once it reaches this peak of the f of x, it's going to be at its maximum velocity, okay? So the fluid flow is fastest at this point, which means that it's accelerating in this region, and then it's going to decelerate down to the fixed point, okay? So as you can see, once x dot starts decreasing in this region, the speed at which the particle is flowing across the x-axis is going to reduce and approach 0. And so you can see that it's almost like something where we start kind of slow, then we really rapidly go through this transition period, and then we decay very, very slowly towards the fixed point, okay? And it's going to take infinite time to actually reach that fixed point. All right, and then the last thing I want to go over, there's a couple more things actually. So first of all is the uniqueness and existence theorem. And I have it written out for y'all here. So existence and uniqueness of solutions. I told you earlier that we're not really going to go over this too much, the theory of it, because that's really reserved for a higher level differential equations course. But we do need to kind of get a picture of when we can know for sure that we do have a unique solution that exists. Because if we don't know that, then the problem that we're trying to solve is ill-posed. For example, in industry or in the real world, if you're dealing with a differential equation, you need to make sure that the solutions exist and are unique before you code a stable numerical algorithm to solve for your solution curves, right? Because almost all of these in practice are not solvable by hand. You need the computational methods to actually generate numerical solutions. So for that reason, existence and uniqueness is very important. Let's just go over this theorem real quick. We have an initial value problem, x dot is equal to f of x, and then we pose this initial condition here. X of 0 is x naught. And so if we know that f of x and its derivative f prime are continuous on an open interval, and this means f is within C1, just a notation for that, on an open interval R of the x-axis, and suppose that x naught is in that interval. So we have here's our x-axis. We have some interval R, could be anywhere along the x-axis, and our initial condition is inside this interval. And we know that on this interval, f of x, here's x dot, f of x is smooth, so it's continuously differentiable and its derivative is also continuous. And now we know for sure that there is a solution. So there's a unique way that this space will evolve in a time interval t to negative t. Okay, so essentially there's some time interval, and if we start at t equals 0, it will basically be from 0 to tau, where there is a unique solution that is well defined and exists, where essentially we can say, okay, this point is going to flow in whichever direction in a unique way, right? And it's completely deterministically defined. And this is very important to know that for certain. And notice that we don't know it for all time, right? So this t is finite. And in fact, if we wait long enough, sometimes we don't have a well-defined solution. For instance, if we have some scenario where our trajectory, here's time, here's x. So if our trajectory, in fact, goes to infinity in a finite amount of time. So this is 4, and we just go to infinity. And we'll see examples of this later on. But the basic idea is there are specific cases where after, in this case, after time equals 4, it's totally undefined, like what's happening here, because because of the properties of this differential equation, we've shot off to infinity so fast that we've literally reached infinity in finite time. Okay. Now let's talk about a real world example, which is really important in the textbook. And this is the logistic growth model. Okay, so the logistic growth model is a model to represent population growth, and essentially it looks something like this. So if we have a population, and we're looking at the rate of change with respect to time, we say that it's essentially it's related directly to the current size of the population by this factor, this growth rate r. And then we're going to multiply this by a carrying capacity term. Okay, so that's going to be 1 minus p over k, where k is the carrying capacity. All right, so when the population is very small, this term is negligible. It's just really close to 1. Okay, so we would just in this instance get something that behaved similarly to just the exponential growth law. Okay, but on the other hand, for this, so this is for small p. And then if we let the population grow and say it approaches the carrying capacity, we're going to have something much different. So when the population approaches the carrying capacity, then this term, okay, is going to approach 0. And then essentially we're going to get a population that asymptotically approaches the carrying capacity k. So this is my population. It's a function of time. We're going to approach the carrying capacity as time approaches infinity. And there's one thing I should note, like the past 2 examples I've actually drawn solution curves instead of the phase plane, right? And so there's a big difference that we should be careful of, which is that there's this phase plane, right? X dot with respect to x, where here I'm actually going to draw the f of x that corresponds to my differential equation, And then the actual behavior of my system is just occurring on this line, okay? And time is kind of hidden. We're just assuming that the flow is occurring like according to some time, right? So like if I started here, started at this population, after some time I would just flow and drift in this direction, okay? However, when there's another diagram that I'm using here, which is the actual like solution curves, okay? So this is where we know specifically how x evolves with respect to time, which is ideal in every differential equation. If we know this, we basically have the thing that we're looking for. So in this case, what I've drawn is carrying capacity, and then say I started a really small population, then I'm going to exponentially grow, and then I'm going to kind of decay towards the carrying capacity like this. Okay. And so this is just population or x of t graph, whatever you're studying. All right. Now, going back to this specific model, the logistic growth model, we can solve this equation explicitly using separation of variables and partial fraction decomposition. However, let's just use the methods that we've learned the past few minutes here. And so I'm going to just graph the phase portrait now, x dot with respect to x. And remember, I'll just write it up here. We're going to have rp f of p is equal to, and I should use p instead of x, I'm sorry. Here's p dot, 1 minus p over k. All right, and now we're going to have this parabolic curve, f of p, and we're going to see that, again, we have negative, positive slope, unstable, stable, and flow is going to be in this direction. It's a stable one, and then on this side, you can see the graph is negative. It's going to flow to the left towards the stable fixed point. Okay, and I'm not going to worry about the region where population is negative because that doesn't make physical sense. Now, what can we identify here? So we can look at this behavior. We can say, okay, we have this carrying capacity, and clearly in our logistic growth model, the population, as long as it doesn't start directly at 0, in which case it would just stay at 0 because there's nowhere for it to go. But as long as the population starts at some positive number, it will always approach this carrying capacity k. And so how does it approach k? Because we know eventually it's going to get there. Well, from this side, we can see it's going to approach very, very quickly. Like if it's way out here, we're going to have some huge negative value for p dot here. So it's going to really, fall really quickly down to this stable fixed point, and then it's going to slow down kind of closer into this region and eventually start decelerating. Now on this side, the region of interest here from 0 to k, at first, if we start really close to 0, we're at kind of a low value of p dot. So we're going to not actually be moving that quickly, and we're going to start accelerating as the value of f of p increases. We're going to accelerate until we reach this point here, the maximum of f of p, which occurs at k over 2. And at that maximum value, the population is going to be increasing at the fastest rate. And then it's going to start decelerating again down in this region and eventually settle down to the carrying capacity. So if we look back at this curve that I've drawn, we see these exact characteristics. We see this exponential growth at first, and then it reaches, this is k over 2 here. It reaches this maximum point of growth at half the carrying capacity, and then it starts to decay down and approach k. Or I guess approach k in a logarithmic fashion. So that's my notes on the population model, which is a useful example. I think that's pretty much it for this chapter. We should see. Oh yeah, there's one last thing to cover. So the last thing that I'll talk about is the potential. So let's find some space here. So the potential function. Turns out the potential function is actually very useful in physics as well. So again, I'm going to bring my differential equation here. And now if I look at a function, let's call it u, okay, such that this is equal to negative partial f over partial x. Wait. I think it's the other way around. Yeah, no, this is the other way around. Okay. It's fine. So u is partial u over partial x is equal to f. Okay, I'm going to delete this. I'm going to crop this part of the video out. Right. So the potential function is defined to be the function such that the... Okay, so let's just talk quickly about the potential function, concluding up this chapter. So we have our differential equation, and now I'm going to define the potential function to basically be given by a function such that the negative of its derivative is equal to f of x. Okay. And I think one of the best ways to illustrate the potential function is just to dive right into the example that we discussed earlier when we have f of x is equal to x minus x cubed. To solve for the potential, I'm just going to set this equal to negative du over dx. And now I'm going to integrate both sides in x. So I get the integral of du over dx to the integral of x cubed minus x dx. So I'm going to get that u is equal to x to the fourth over 4 minus x squared over 2 plus some constant of integration. Now for our purposes, this constant doesn't actually matter because we're going to view u as almost like this hill that is just giving us more qualitative insights about the evolution of the system. So it's really just a tool for helping us model what we think is going to happen rather than get like an analytical result. So let's graph the potential function here. X, u. So the potential function looks like x squared near the negative x squared near the origin, and then x to the fourth starts to dominate for large x. So it looks something like this, and this is what we call a double well potential. Now what I've drawn here is the specific case when c is equal to 0, but it doesn't really matter. Now observe that what we can learn from the potential is that essentially if we look at a trajectory or flow along the line, we can view it as essentially a ball rolling down this hill, and the trajectories will always descend down the potential, okay? And this is because of the fact that as we defined the potential earlier, we have the potential, the derivative of the potential is equal to negative f of x, which is equal to negative x dot. And so if we look at the change in potential with respect to time, okay, by the chain rule, this is the change in potential with respect to x times the change in x with respect to time. And so now, plugging in this first equation for du over dx, we have negative x dot squared, because this term is also an x dot, okay? And so we can see that this is strictly less than or equal to 0, which means that the system will always evolve in such a way that the potential will decrease with time, okay? So if we look at the time evolution of this system I've drawn here, it will have to evolve such that the potential will decrease. So it will always roll down this hill and eventually settle down at the bottom, which actually corresponds directly to our stable fixed points here. Okay, so it turns out that local minima of the potential function correspond to stable fixed points, and local maxima of the potential correspond to unstable fixed points. And there's also like a mathematical reason for this, that if we just plot f of x is equal to x minus x cubed here, we're going to note that it's going to align very nicely. It's going to look something like this, where this is stable, unstable, unstable based on all the analysis we've done so far. Now, of course, these two are very different things. When I plot f of x, I can look at the fixed points, which are the intersections with the x-axis, whereas the potential, the fixed points occur precisely at the minimal values of the potential and at the maximal values of the potential function. But you can see that these two things coincide perfectly. And if you start to think about why this might be the case, well, if we have a derivative, okay, so essentially the derivative is equal to 0 at this point, right? And now if we, so if we look at this partial u of a partial x term here, this is our f of x. So when f of x goes to 0, wait, why is this the case? Yes, okay. So when f of x goes to 0, okay, we have critical points of the function, and notice that this corresponds also to critical points in u, because it's going to occur precisely when du over dx is equal to 0. And so therefore we have that during that fixed points will occur at the maxima and minima of the potential. One common mistake that people make is they kind of visualize, maybe they saw this in like a modern physics or quantum mechanics course, and they visualize the time evolution of this system incorrectly, where they kind of think of this ball as rolling down this hill, and then it might oscillate like it would in like a real physical system where it kind of rolls up the hill and rolls back down. But this is not the case at all in this system that we're studying, because remember, the flow is single directional. So you can never have a system that flows to the right and then all of a sudden flows back at some later time. That's not possible because f of x is a single valued function. If instead we had x dot is equal to f of xt, things would be totally different. Now we actually could have motion that moves backwards and flows in on itself. And so then we could have periodic oscillations, right? But this is totally different from the system that we're analyzing, which is just an autonomous system with no explicit time dependence, okay? And now, so I just wanted to emphasize, do not make the mistake that this ball is like oscillating along the potential well. It's just going to always descend down the potential and just come to rest asymptotically approaching the local minima of the potential function. Okay. And yeah, I think that's all I wanted to cover on this subject. So I'll conclude the chapter here, and I appreciate your patience. I'm just barely starting to do these online lessons, but we'll do the next chapter tomorrow. And if you have any feedback on how I could improve these lectures, please let me know. I know I like move around a lot and I like zoom out a ton, so I'll work on that. One last thing before we go, I'll just quickly note that in this system, x dot is equal to f of xt. So in a non-autonomous system, we can do a change of variables, which basically set t is equal to x2 and x is equal to x1. X is equal to x1. And then we just have x1 dot is equal to f of x1, x2, and x2 dot is just equal to 1, because we're just taking the derivative of t with respect to time. And so we can rewrite this non-autonomous system as an autonomous system of second order, Okay, not second order, but second order. So essentially, by increasing the order of the system, by increasing the number of variables and the dimension of our phase space, we're actually able to get rid of the explicit time dependence, and therefore all of the analysis that we'll do in the later chapters of these higher dimensional systems will definitely apply. You can use it to solve lower dimensional systems that are non-autonomous by simply expanding the dimension of your phase space. This is a really important concept that's also used for second order, second degree. I need to get those terms properly aligned. But yeah, second degree differential equations. We have x double dot plus, let's just say mx double dot plus kx is equal to 0. So this is just an undamped oscillator. So I don't know if y'all are familiar with like an undamped oscillator, but it just looks something like this. And essentially, this equation is of second degree, and so it's a bit more complicated to solve than if we just had a single degree of the derivative. Now, the degree of the system refers to the highest degree of the derivatives, whereas the order of the system, this is wrong. This is so wrong. Okay, so after thinking about it for a second, the best way to explain why these coincide perfectly is that every critical point of the potential function needs to have a derivative of 0, right? That's a concept we learn in calculus, that every maxima or minima will have a slope of 0 at that point. Well, that's going to, since u of x, when we take the derivative, is just negative f of x, whenever there's a 0 of f of x, i.e. at a fixed point, right, we're going to have a maxima or minima of the potential function. So therefore we can see that, yes, indeed, all of our fixed points are going to directly correspond to critical points of the potential function. Now, the last thing I do want to discuss briefly is that if we just look at the time evolution of the system, it's a common misconception that this thing might roll back and forth, and like roll down the hill, then kind of roll up and then slide back down and such, and oscillate at the well of the potential. And that can happen in like quantum mechanics or in physics, but they're talking about totally different systems that are not homogeneous or like autonomous as we are. So in this case, x dot is equal to f of x. This is an autonomous system. There's no time dependence. And so like I explained earlier, you can never have a situation where you have flow along the line in one direction and then it reverses back, right? That's impossible because this f of x can only take a single value. So it either has to be flowing, to the right or to the left at a certain point. It can't do both at different times. So because of that, this ball will never oscillate in the potential well. So this is totally wrong. Instead, it's just going to asymptotically fall down and just approach a stable rest position at the bottom of the basin here. So it's not like physically logical, but this is how the system works. If I were instead to give you a more complicated equation, if I introduce time dependence to this function, okay? So for example, say I said sine of x plus t. F of x t is equal to sine of x plus t or something. You could pick anything you want. The idea here is that this system now has enough degrees of freedom that oscillations are in fact possible, okay? Because I could be flowing one direction at some time, and then at a later time, my function could take a different value because it explicitly depends on t. And so I could have, in this case, oscillations, and we see that in physics. In a lot of cases, you'll see double well potentials where you actually do have oscillations at the bottom of a well. Now, this function, this system, we're not going to look at it. We're not going to analyze it in this course. Okay, which might be like, what? Why are we not doing that? Well, essentially, there's a trick that we can use, which is that we can expand the number of equations of the system. Okay, so the order of the system. And by doing that, by expanding the phase space by an additional dimension, we can get rid of the explicit time dependence. Let me just show you how that's done. So all I'm going to do is I'm going to set x2 equal to t, and x1 will just be equal to x, as before. So I have x1 dot is now a function of x1 and x2, and x2 dot is just 1. Derivative of t with respect to time is just 1. So I'm left with this system, which doesn't have any explicit time dependence, but we now have increased the dimension of the system by 1. And so we're going to learn how to analyze systems of these higher dimensions, but we're not going to worry about the time dependence because we can always just expand the dimension of our phase space to account for any time dependence that we might have. This is a really useful trick to know about. It also shows up in higher degree equations. So if we have like x double dot mx double dot plus kx is equal to 0, this is the familiar undamped oscillator spring mass system. So in this equation, we can actually set x1 equal to x and x2 equal to x dot, okay? Or the way that Strogatz expresses it, I like, which is essentially x2 is equal to x1 dot. And then if we set if we set x2 equal to x1 dot, then x2 dot is just x1 double dot, okay? And this is going to be our x1 here. And so this is just equal to negative k over m x1, okay? And so we're left with an x1 dot equal to x2 and an x2 dot equal to negative k over m x1. And so now we've created from this original second degree equation, but we only have an order of 1, right? So we only have one differential equation we're working with. We've now expanded the phase space we've expanded the degree of the variables we're working with to create, this degree in orders is mixing me up here, but essentially we've reduced the degree of the system to a degree 1 system, but we've increased the order to 2 equations. So this is a super useful method throughout differential equations, and because of it, we're not going to worry about higher degree equations because we can always just reduce them down by the proper change of variables to just a higher order system that's all first degree. All right, that's all for chapter 2, and I'll be sure to include the relevant exercises that I find to be the most challenging and interesting from chapter 2. And yeah, thank you for your attention. I will see you next time, tomorrow hopefully, for chapter 3. So I hope you're able to follow along for that. Have a good night. So we've expanded the order of the phase space in order to reduce the degree of the equations we're working with, okay? So just some terminology. Degree is the highest degree of derivative. So previously we were working with a second degree system, but it was first order. So our highest degree of our derivative was 2. And then the order / dimension is just the number of dependent variables, okay, or variables of study. And as such, we will have however many, if we have like an nth order system or an nth dimensional system, that has to consist of n first degree differential equations in order to fully describe the system, right? Because we need a differential equation. Kind of think about linear algebra, how you need if you have like an nth dimensional space, you need n vectors to span it. Same thing here. If we want to analyze the trajectories of an nth of like n dependent variables, we need a set of n equations. And so yeah, this is a common trick, and it allows us to use the tools that we've learned for first degree but second order systems to solve equations of higher degree, but like say a single differential equation, but it's of a higher degree. Okay. So that's all for this chapter. I'm skipping section 2.8, which is the numerical methods section. It will be of use later, and we may need to review it at some point. But yeah, I hope that you enjoy this book, and I hope you learn a lot. And I recommend that you do some of the exercises along with me. I'm going to post a supplementary exercise video for each chapter that I do, and I plan to do a chapter of this book every day for the next 12 days, excluding Sunday. So, hope you all have a great night, and take care.